Hey everybody, Mr. Brooks here again. So today we're going to cover section 4.3. This is homogeneous linear systems. So in this particular section, we are going to develop methods for solving linear systems, similar to those approached with scalar equations. So again, we talked about the definition of what a scalar equation was. It's everything that we dealt with in chapters 1, 2, and 3. So that way we have a terminology difference between the two. And also we talk about the system of differential equations in this case. But what we're going to do is we're first going to investigate the properties of homogeneous linear systems, because that's how we've always started things off with, because they're really nice differential equations to work with. And then we're going to develop a method for solving those with a constant coefficients. Again, we're doing a step-by-step process here. And then develop methods for solving non-homogeneous systems when we get into that. So for this particular one, we're just going to look at the very beginnings of what a homogeneous linear system is, get into a couple of principles and theorems that pop up out of this, and then also some matrix identities that pop up as well. So the first of all, the system of differential equations, y prime is equal to pt, piece of ty. Again, these are bolded letters. That's a little bit harder to see in this situation. Defined on some interval AB where t is included. This notation here is just saying t is an element, or t is in this particular interval. And so this is called a homogeneous linear system. So a first, and let's be a little bit more precise with that, is a first order homogeneous linear system. Again, we're going to be dealing with, in chapter 4, just dealing with the first order homogeneous linear systems. So everything is going to be of the form of the first order for that part. All right, so that's our basic definition here. This is also included in the definition as well. The vector function y of t, okay, that's where it's got a singular column within rows, and the matrix p of t were defined back in 4.2. So everything that we've talked about, this has got the p11, p12, and so forth. And when we switch over to talking about constant coefficient matrix, we're going to put an a in here, so that way there is a notational difference between the two as well. So right now this is still talking about general, where we could have functions of t pop up. So the very first thing is now we talked about that, we're going to talk about the principle of superposition. And so this one is the same type of idea that we've dealt with in the past, except we're now going to be dealing with matrices in that case. And so when I write up the next piece here at the beginning, so we're going to let y1 of t, y2 of t, and so forth, y sub n of t. And these are going to be bolded because these guys are still vector functions. Okay, so these guys have multiple functions attached on the inside of them. So these again are vectors that we're going to have. So we're going to let these be any n solutions, so there's n of them, of the homogeneous linear system. And our homogeneous linear system we've defined up here as well. Okay, so it's everything satisfying this particular system here. Okay, then for any constants C1, C2, up to C sub n. Okay, so for any of those types of constants, the linear combination C1, C1y1 plus C2y2 plus so on up to C sub n, y sub n. Again, these functions here are these vector functions represented here. Okay, then the linear combinations of this particular form is also a solution to the homogeneous linear system. Okay, and this is something that we talked about with scalar scalar differential equations. So this is that same idea. So the superposition principle here is just saying, hey, we have a bunch of solutions here, and we can actually find more of those by coming up with linear combinations of those guys. All right, and again, C1, C2, and so forth, these guys are constant values multiplying these particular vectors. All right, so the next step. Next definition that we're going to get into is, well, if we're talking about principal superposition and how to solve these homogeneous linear systems, then the next step is talking about fundamental sets, which is what we talked about previously in chapters 2 and 3. So we're going to continue that idea, except now extending this out to linear systems. So the set of n solutions, and again, these are these vector functions. So I'm going to try to bold these as I go, so then that way we can see that these are no longer just individual scalar functions, but vector functions. All right, so the set of n solutions of these guys is called a fundamental set. Of solutions. If, so, and this is again where we're getting to, well, what does a fundamental set mean? If every solution of the system can be written as a linear combination and again, y of t is equal to c1 y1 plus c2 y2 plus so on up to c sub n y sub n. And again, these are these vector functions defined at the beginning. So if we can write those as a linear combination, this linear combination should look familiar to our other forms that we've seen, but now we're dealing with these vector functions. This is called the general solution. Of our homogeneous linear system. Okay, and so what do we need? How do we talk about that it forms a fundamental set? So once we have these n solutions, what's that next step? Well, you probably guessed it already. That's what we're going to deal with. Well, how do we know we can do this? It's the Wronskian. So once again, we will use the Wronskian to determine if it forms a fundamental set or not. So we will use the Wronskian to determine if the set of solutions forms a fundamental set. So in that case, we need the Wronskian to be non-zero. Okay, and once we have that, then we can come up with the general solution to that particular system. Now, the hard part here is we are no longer dealing with individual scalar differential equations or solutions for that. These guys are represented by matrices. So we need to first look at a couple identities to help us with figuring out the Wronskian for that part. And so we are going to introduce another Greek letter, psi, here in just a second. So, before we get into that, some important matrix identities. All right. So the first thing that we're going to talk about, and actually this is really the biggest one, is notational things that are coming up here. So we're just doing some housekeeping here in just a second. So we're going to talk about the column form for matrix vector multiplication. Okay, so this is what we're going to be talking about. So here we're going to let A be an m by n again row column matrix, and let X, here I'm going to try to stay away from doing cursive X because I wanted to distinguish between the two. So whenever you see a bolded X or one that's using the stick lines for that, instead of having the curl to it, that represents a vector function, and I'm going to try as best as possible to keep that notation going through. So this is going to be an n by 1 vector. All right, so what that looks like is A is going to be in this format. A11, A12, so forth, up to A sub n. Sorry, A1n. And this is going to go down to AM1 because we have m rows, all the way over to AMN. So number of rows, number of columns. And X, as best as I can here, is going to be X1, X2, X sub n. So notice that the notational difference is very slight with my handwriting, but if you saw this in typeset, this is a bolded X, and these are little script X or math font X's for that. All right. We can represent A in a column form. So column form. That looks like the following. As A is equal to, and here notice I'm still using capital letters here. What this is this is representing each column of this matrix. So A1 represents this column of A11, A21, A31, A41, all the way up to AM1. A sub n is AN1, AN2, AN3, AMN for that part. Okay, and again, just to have an example there, when you're going through this, so A1 is equal to A11, A21, A31, AM1. That's what that looks like. Okay, so moving on. So again, just because of the nature of what we're dealing with, since we're dealing with systems and matrices, we have to be careful about our notation and also about the multiplication when it comes through this. Okay, then the matrix vector product and that's represented as AX, okay, is equal to the linear combination the following. AX is equal to x1a1 plus x2a2 plus so on up to x sub n, a sub n, in that case. So that's our linear combination, okay? So in that case, we multiply each of these terms by a1, a2, a3, and so forth, all right? And these actually should be, to help with the notational difference, these are our script x's, where these guys are coming from, okay? So that's what this is going to look like. So for example, so again, think if I just left this up here and be like, oh, there you go. So let's look at an example real quick. Now again, every time that I write an example up here, my suggestion for you guys is to pause the video, try it out on your own, or if you don't want to pause the video, that's perfectly fine. You can hear me ramble through it right off the bat. But try to pause the video, test it out on your own, see what you can come up with, and then play the video. All right? So then that way it's similar to what we've dealt with in class. So consider the homogeneous system y prime is equal to ax. And here we're going to say t is somewhere in between negative infinity and infinity. So yeah, I've got a pretty broad interval here. All right, where a is equal to the matrix 0, 1, 0, negative 6, 5, 0, and 0, 0, 1. Okay. I want us to verify the following. That y1, which is equal to e squared of t, 2e 2t, 0. y2 is equal to e cubed t, 3e cubed t, 0. And y3 is equal to, so notice here I have 3 by 3 matrix, so I'm going to have 3 solutions with this. Okay. And 0, 0, e to the t are solutions. Okay. So that means when I plug these into our system here, when I multiply this by the matrix, I'm going to get the derivative of each individual one of these out. So what I'm doing is, first of all, this is what I'm going to do. So here's my solution. So let's walk through this process. All right, so this would be where to pause. All right. So now if you're back with us, if you're not, then that means you stopped the video, so you need to press play again. Of course, you didn't hear that part. So I want to see, so y1 was equal to e to the 2t, 2e to the 2t, and 0. So that means y prime should be 2e to the 2t, 4e to the 2t, and 0 when I plug y1 in. So to check that, all right, so here's our check. All right, so we have 0, 1, 0, negative 6, 5, 0, and 0, 0, 1. We're going to multiply it by this matrix of e to the 2t, 2e to the 2t, and 0. When I multiply that in, and that's a 0, not a 6, so let me fix that. All right, so when I multiply, let's go through this multiplication process together. Again, this is good review for getting back to the swing of things with matrices. So row times column, that's going to be our first element in this column. More firm here. So in this case, we have 0 times e to the 2t plus 1 times e to the 2t. And then 0 times 0. All right. The next one, we're going to have negative 6 times e to the 2t plus 5 times 2e to the 2t, so that's going to be positive 10 e to the 2t, and then 0 times 0, so plus 0. And then lastly, we're going to have 0 times e to the 2t, which is 0, 0 times 2e to the 2t, which is 0, and then 1 times 0, which is 0. So 0 plus 0 plus 0. All right. Again, this is a pretty easy format, but it's not bad. So 2e to the 2t is our first term. Our next term is going to be 4e to the, I even said that and wrote 10. So make sure that you write 4e to the 2t and then 0. So yes, this is a solution. So that's good. So that's check mark number 1. All right. Yeah, I'll throw the next one in. So y2 prime. So let's look at that guy. So take the derivative. So we're going to get 3e to the 3t. Then we're going to get 9e to the 3t. And then we're going to get 0 out. So here's our check. Again, 0, 1, 0, negative 6, 5, 0, 0, 0, 1, times our original y2 here of e to the 3t, 3e to the 3t, and 0. All right. So again, row times column. So this row times this column here. So 0 times e to the 3t is 0. 1 times e to the 3t. And that's e to the 3, or 3e to the 3t. And then 0. Then we're going to have negative 6 times e to the 3t. Plus 15, because 5 times 3. And then 0 times 0, so that's 0. Okay? And then on the bottom one, we're going to have 0, 0, and 0. So combining like terms, we get 3e to the 3t. Negative 6 plus 15, that's going to be positive 9e to the 3t, and 0. Looking back at our derivative, yes, that's exactly what we wanted. So these two are solutions. All right. Moving on. We're almost there. So now we need to check the third one. y3 prime is equal to, well, let's take the derivative. Well, that's easy. 0, 0, and then e to the t. All right, so our check here, we're going to have, and we're already kind of listed in that format. So our check is 0, 1, 0, negative 6, 5, 0, 0, 0, 1. Multiplied by our y3 over here. So what we want to happen is get an exact copy of y3 because that's the derivative as well. All right. So when we multiply, this was going to be pretty hopefully straightforward. 0 times 0, 1 times 0, 0 times this. So we're going to get a 0 for our first one. Negative 6 times 0, 0. Plus 5 times 0, which is 0. And 0 times e to the t, which is 0. And then our last one, 0 times 0 plus 0 times 0 plus now finally 1 times e to the t. And yes, so we have just verified that all three of these are solutions. Okay, so now that we have an n number of solutions, so this is a 3 by 3, we have 3 solutions. Let's see if we can come up with the general solution. Well, in order to do that, we need to talk about, well, does this form a fundamental set? Do these 3 form a fundamental set for that part? All right, so this is where we're going to get from theorem 4.2, which is talking about the principle of superposition. All right, so since these guys are solutions, thus, by the principle of superposition here, by theorem 4.2, all right, we know y of t, which is equal to c1y1 plus c2y2 plus c3y3 is also a solution. So since we know that those 3 guys are solutions, that any linear combination, that's again coming from the principle of superposition. Okay. for any choice of C1, C2, C3 is also a solution. So that's where that's coming from. Okay, so we know that this linear combination is a solution. Is it the general solution? So this is where we're talking about, does this form a fundamental set? Does the Wronskian equal non-zero for that part? Okay. So by our matrix identity, we can write, or rewrite, sorry, this linear combination so notice what we do up here. So we have our linear combination is equal to the matrix vector product, okay, in the form. So it's a good thing I left that one up there. Y of t is equal to psi, and let me write a better one up there. So yes, we are using a new Greek letter here. So it's going to be psi times this constant value here, c, okay, where psi is equal to the column form of y1, y2, y3, which we can express in terms of a regular matrix here, a 3 by 3 matrix of the form. All right, y1, its column is represented by e to the 2t, 2e to the 2t, and 0. y2 is represented by e to the 3t, 3e to the 3t, and 0. And then y3 is represented by 0, 0, e to the t. All right. And c here is just equal to the vector represented by c1, c2, and c3. So again, we've taken this linear combination, rewrote it as a matrix vector product, okay, represented by these two this matrix C and this vector. Okay. Well, we have that. Well, that's how it looks, but is that the general solution? So again, I keep wanting to illustrate that. So let's talk about the Wronskian here in just a second, what we're going to be dealing with. Okay, and I see a 3 by 3 matrix already, which means I'm going to have to deal with minors for the determinant, which is okay. We can deal with that. And so this will be a little bit of extra practice. And there's some nice observations that we'll use when we get there. Okay, so let's stop the video for right now. So there's going to be an intermittent pause. We're going to erase all of this mess up here, and then we're going to talk about the Wronskian and then come back to this solution here in just a minute. Hey everybody, welcome back. So now we're into part 2 of this video, which is, so in that previous problem, we found out that we had 3 solutions, and then by the theorem 4.2, which is the superposition principle, we were able to say any linear combination is now a solution to that, which is great. But does it form a fundamental set? So this is where we need to talk about the Wronskian real quick and getting used to developing it for these systems of linear equations and how we go about operating. And the operation is not much different. It's just terminology might change. And then we saw previously that there's a psi involved. And that is, again, is to help with notation for that. So let's consider, again, just to generalize this, and we will go back to our problem. Consider the IVP, and this, again, is dealing with a linear system. So y prime is equal to p sub t of y. Again, this is a matrix of some form an n by n matrix. This is our vector here, y, and then we have initial value problem. Y sub t of 0 is equal to y sub 0. These again are vector format as well on some interval from a to b. And then we're going to let this set be a set of n solutions. Again, these are vector functions that we have here. All right, so the Wronskian determinant. Well, the Wronskian determinant is calculated just the same way that we would do this. So W of t is equal to the determinant of this particular column form that we have here. Which is equal to the determinant. And I've always dealt with this. I know that if we take, it looks like absolute value symbols, but it's taking, that's still the determinant for this. So here, y1 is represented as this column, y1, 1, y1, 2, so forth up to y sub n1. Okay, sorry, 1n. Reverse that. Oh, sorry. Let me fix that. I butchered my own expression here. So this is y2, 1, so forth up to y sub n1. Okay, again, row column is how those numbers are represented. y2, so this is y1, 2, y2, 2, so forth. And this goes up to y sub 1n and down to across to y and n. So it's going to have n by n terms. So a 3 by 3 obviously has 9 terms. A 4 by 4 is going to have 16 terms, all that fun stuff for that part. So we take the determinant of this. So what we're going to do is we're going to have this to help us with notational difference. And I'm not going towards that theorem yet, but just to help us with that. So we're going to set psi equal to this particular column of y1, y2, up to y sub n. Okay? So that means then the Wronskian of t is equal to the Wronskian of the determinant of psi. So that's all this is doing. So notationally wise, when you see this in the book, that's what it means. So we're just representing this column here form as psi. That's all that is. So it's nothing new or major. It's just adding in extra notation. So then that way we can truncate this down. So we can look back and be like, okay, this is what psi means. So we can later talk about it without having to re-illustrate it every single time. So that's all that is. So the big thing is if the determinant of psi is not equal to 0, which is, again, saying that the Wronskian is not equal to 0, for all t in AB, okay, then we can say that the columns of psi forms a fundamental set. Okay, sorry, forms a fundamental set of solutions. So we've seen that before with chapters 2 and 3 when we're talking about the Wronskian there. And we call, and this is where we do have a new definition here. We call psi then, psi of t, the fundamental matrix. So psi, if we find out that its determinant is non-zero, then it is the fundamental matrix of the system. So a couple of ways to say that we do form a fundamental set with y1, y2, y sub n, or we could say that no, this matrix is the fundamental set for the system, or fundamental matrix of the system. The general solution is given by the following. Again, the general solution of the system is given by y of t is equal to, again, this linear combination of y1, y2, y sub n, and then we can rewrite that in our matrix form. So c1, y1 plus c2, y2 plus so on up to c sub n, y sub n. This is equal to the matrix y1, y2, y sub n times the constant vector here, c1, c2, c sub n. So that's our format that we can use for this, okay? So again, it's a 1 by n times n by 1. So therefore, the multiplication of that is going to give us this linear combination here. All right, so now we can talk about the next piece. So we are going to get into our example again, but again, the Wronskian is exactly the same process that we've dealt with before. As we go up in the number of differential equations for the system, yes, we are going to have to get in more and more complicated calculations for the determinant, which I'm going to show a couple. So then that way I'm not leaving you high and dry without examples for that part. But again, psi here is just saying, okay, this is our fundamental set if our determinant is not equal to 0. So that's the big thing. And we could say psi, if we wanted to, is the fundamental matrix. So if you see that on a test or homework or anything like that, or the final, the fundamental matrix is just the fundamental set of solutions in matrix format. That's all that is. Okay. All right. Theorem 4.3. First of all, we have our hypothesis here is let y1 up to y sub n be a set of solutions of a linear system, and let psi be the n by n matrix where y1 and whatnot, these are vector functions here. So with those guys, once we have that format, then calculating this into there, then the set y1, y2, y sub n is a fundamental set of solutions if and only if, now if you want mathematical shorthand, that's that IFF that we've talked about in previous lectures. So if and only if, so this is a two-way street, okay? So this is a fundamental set of solutions if and only if the Wronskian of psi, meaning the determinant of psi, is not equal to 0 on AB. So what's an if and only if statement? Well, these guys are awesome in mathematics because if you can set up an if and only if statement, then it's a very, very sound theorem. However, it can become extremely hard to prove one way or the other. So what this reads as is if this is a fundamental set, then the Wronskian is not equal to 0. The other way it reads is if the Wronskian of psi is not equal to 0, then this forms a fundamental set. So that's what an if and only if statement is. It's read both ways, so forwards and backwards. So that's what that means. Okay, so that's cool. If we can show that the Wronskian is either not equal to 0, or if we're told that this is a fundamental set, then the Wronskian has to be not equal to 0 for that case. All right. So let's go back to our particular example that we were dealing with before this. Okay. So, consider our IVP that we talked about previously. And now we're making an IVP in this case. And again, it was on this infinite interval where A is equal to the constant matrix here of 0, 1, 0, negative 6, 5, 0, and 0, 0, 1. And y sub 0, so our initial values when t is equal to 0 is 3, 7, and 4. All right? So, from our last example, we know y1, which is equal to e to the 2t, 2e to the 2t, 0. y2 is equal to e to 3t, 3e to the 3t, 0. And y3, which is equal to 0, 0, e to the t. We know that these guys are solutions. So we've already proven that part. All right, so here's my two pieces that I want to do. Part A, I want to show that y1, y2, y3 forms a fundamental set. Of solutions. So what do we need for that? So start thinking about that before you pause the video. And part B, I want to solve this IVP. Okay, I want to find out what that C1, C2, and C3 are for these specific values when t is equal to 0. All right. Again, what do we need in order to, and we just talked about this too, so your answer should be quick when I ask it. All right, so what do we need to show that this particular set of y1, y2, y3 forms a fundamental set? Well, you're probably yelling at me now, like we already know this, is that we need to show that the determinant is not equal to 0, okay? So, here's our solution. This is part A solution right now. So again, previously we wrote our linear combination of y1, y2, y3 as y prime is equal to psi of t of c, where psi we represented was equal to y1, y2, y3, and c was equal to c1, c2, c3. Okay, so that means we need to look at the determinant. So this is calling in theorem 4.3. Okay, the Wronskian, which is equal to the determinant of psi of t. All right, so we're going to look at the determinant of e to the 2t, 2e to the 2t, 0. y2 was e to the 3t, 3e to the 3t, 0, and 0, 0, e to the t. All right, so we take the determinant of this. So one thing, when you're finding the determinant, you could choose a row or a column to come up with this. And the best thing to do is look for either a row or column that has a bunch of zeros in it, because then that makes life a lot easier. So the nice thing about this one is I'm going to use the bottom row to determine my determinant of this particular system. The nice thing is when I'm dealing with these two, those minors go away. So the only thing I have to do is say e of t times its minor for this particular problem. So this is equal to, now if you wanted to see that, that's fine. So I will write that, but just to show you what I mean by that. So we'd have 0, so if I chose this, then I'd have the determinant of this minor here. So it'd be e to the 3t times 0 minus 3e to the 3t times 0 minus, okay? So, and again, when you're going through this, the determinant, no matter how big it is, it always alternates signs, so it starts positive, negative, positive, negative, positive, negative. So if we had a negative value here, then this would become plus. Okay, so it's opposite sign. So normal, opposite, if we wanted to calculate that. 0 times then its minor, which is e to the 2t times 0 minus 2 e to the 2t times 0. And then finally, what we're actually looking for is plus e to the t, so that's a plus sign, times its minor, where all the good stuff is happening. So e to the 2t times 3e to the 2t, well, that's 3e to the 5t minus 2e to the 2t times 3e to the 2t, or e to the 3t. So that's going to be 2e to the 5t. Well, when we calculate this, this goes to 0, that goes to 0. This becomes e to the 5t times e to the t. So we're going to get e to the 6t out of this, which is not equal to 0 for all t. Now, this again is a mathematical symbol saying for all, so it's upside down capital A, or a V with a slash through it. So that means for all. So I'm going to put that in there as well. So don't freak out when I throw that in there. But that's what it represents. And so that's for all t on the interval from negative infinity to infinity. So what we have just shown is that this forms a fundamental set. Okay? So thus, by theorem 4.3, the set y1, y2, y3 is a fundamental set. Okay? So, we have just shown part A is to show that this forms a fundamental set. Now, part B is the fun stuff. Okay? We need to solve the IVP. This is going to require some fun matrix stuff, to say the least. So, now that I'm going to give you a second to take a screenshot of this, copy it. All right. So now that we've shown this forms a fundamental set, that means we can have our general solution. Okay. That's the cool part. Now I might have to erase this here in just a second, but don't worry about that right now. So, we want to solve the IVP for when t is equal to 0. So that's the big thing. So this is part B. All right. So we have y of 0 is equal to psi, this fundamental matrix evaluated at 0, times c. Okay. Well, in our case, we know that y of 0 is equal to 374. Okay, so y of 0 is equal to 374. We know what the fundamental set is. Okay, so our fundamental matrix evaluated at 0. When we do that, so let's write down these pieces. This evaluated at 0 was this column evaluated at 0. So notice we're going to get 1, 2, 0. 1, 2, 0. Then we're going to get 1, 3, 0. And then we're going to get 0, 0, 1. All right. C was equal to C1, C2, C3. So we're figuring that guy out. And y of 0 is equal to this 3, 7, 4. So that's what's known. Okay. Now here comes the fun piece. Okay, there's a couple ways that you can deal with finding the inverse, and we're going to talk about why we need the inverse here in just a second. So what this means is I need to find out what C is, what the C1, C2, C3 is. Well, C, if I solve this, is Tsai inverse of Y, of 0. Okay? So that's one way I could solve this. There's a couple ways I'm going to solve this. I'm going to show you both ways. One way is just the old school setting up an augmented matrix and solving that way. And then the other one is more linear algebra based, where we find a determinant, find the transpose and the adjoint matrix for all that fun stuff. So I'm going to show you the that part first. Actually, I'm going to show you the augmented matrix one first because that one is a little bit quicker and also takes up probably like one line of paper if you do it correctly, so nothing horrible comes out of it. So we're going to find the inverse of psi here. So there's a couple ways that we're going to do that. Okay, so psi of 0, because we need that in either situation. All right, so the first way is augmented matrix. Okay. Well, it's an augmented matrix with the identity matrix is what you do. Okay. So we set up psi, which is 1, 1, 0. And let me even put that in here. All right. And so what we want to do is we want in some set of row operations, we want this to become I, and then on the right-hand side is going to be our inverse of that matrix. So using some sort of row operations. All right. So 2, 3, 0, and 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. So some of these can take up a lot of time. This one's really quick and easy when we get there. What we want to do is row reduce the left-hand side, and that is going to give us our inverse on the right-hand side. So the nice thing is row 3 is already in that format that we want, so we don't want to mess with him at all. The nice thing is we got zeros up here, so we don't have to subtract anything or add anything with row 3. So I want to get a 1 up here, a 0, a 1, and I want these to be 0. Well, the first thing I can see here is if I subtract 2 of row 1 into row 2, we're going to be good for that part. So I'm going to say row 2 minus 2 row 1. Okay, so the reason I'm doing that is 1 is a mental check when I look back through my notes and say, okay, what the heck did I just do? And 2, this gets you used to bookkeeping on what you need to put in. So I've not done any row operations on row 1 and row 3, so I can go ahead and write those down. Okay. Now let's look at the end result for row 2. Well, 2 minus 2 times 1, so 2 minus 2, well, that's going to be 0. So that's exactly what I wanted there. So we already have our column the way we want it. And then I have 3 minus 2 times 1, so that's going to give me 1, and then 0. And then this is where a lot of people, I've had issues with some students when they dealt with matrix row reductions before, that they forget the right-hand side of this augmented matrix. You want to mess with this because this is how we get there. All right, so I said row 2 minus 2 row 1, so there's going to be a negative 2 here. The nice thing is I just have a 1 here and a 0. Okay, so nothing bad there. All right, so we're actually almost there because I need to get rid of this 1 here, and then we'll have the identity matrix on the left-hand side and our inverse on the right-hand side. Okay, so how are we going to do that? Well, I just need to subtract row 2 from row 1. and that should give me everything, which means I did not mess with row 2 and row 3, so go ahead and write those down. And when you're doing this, my suggestion is to, anytime you don't mess with a row, to go ahead and write it down, so then that way you're kind of solidifying the fact that, okay, I didn't mess with those guys, it's just a copy and paste from the previous matrix. Okay, so row 1 minus row 2, so we're going to get 1 here, we're going to get 0, and we're going to get 0. And then I've got 1 minus negative 2, so then that's going to give me positive 3. And then I'm going to get 0 minus 1, so that's negative 1, and then 0 here. So this right here is Tsai inverse, which is 3, negative 1, 0, negative 2, 1, 0, and 0, 0, 1. Okay, so that is the first approach to figuring this out. So it only took a couple steps and you're done. Now, when you get into larger and larger matrices, this becomes a little bit more difficult to deal with. The nice thing is, the cool part here, is if the determinant is not equal to 0, then it has an inverse, which means if you're getting to this particular point, you know at some point down the line, it might take a ton of row reduction steps to get there. At some point down here, you will have an inverse come out of this. So that's the good thing about this part. We've already proven for all values of t that psi has an inverse. So that's the cool part. So I keep saying cool part, and you're all like, yeah, okay, whatever. So that's one way to find it. The other way to find it is not as fun, okay? All right, so what we do is we find the cofactor of psi. Then our next step is to find the adjoint of A, or of psi, which is equal to, so when we talk about cofactor, it's given, from what I've seen, so I looked into some other books just to make sure my notation was right. A capital C would represent the cofactor matrix of psi. And we're going to talk about, well, what the heck is that thing? And then this is, once you find it, the adjoint of psi is actually the transpose of the cofactor matrix. And I am going to go step by step. And then finally, the inverse of psi is equal to 1 over the determinant of psi times the adjoint of psi, or C transpose. All right, so first of all, this is a couple-step process. So I'm going to label this step 1, step 2, and step 3. So step 1, so step I, is find the cofactor, this capital C. So this is our 3-step process, okay? So finding the cofactor is actually just dealing with the minors of the original matrix. And when we're talking about the minors, we're actually only dealing with the determinant inside of each of those minors. And that's how you calculate each individual piece. So how you do that, and I'm going to try to be as thorough as possible with this process because, one, it took me a while to remember this, and two, it's probably been a while for you guys, so trying to go through this step by step is the most important part. So we look at the first value here. All right, I mark off these two, and I'm only going to deal with the determinant of that matrix there of 3, 0, 0, 1. Okay, so that's going to be the first term. 3 times 0 minus 0 times 0. Oh, sorry, 3 times 1. My bad. Already had it off on this wrong step. Okay. Next, so when you're dealing with this at the 3 by 3, it's plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay. So I'm going to have, and I'm going to put boxes around this. Negative. So it's not subtraction. This is its own term, minus the determinant of the matrix 0 or 2, 0, 0, 1. Okay, so we take this, we block off that, we're left with these two pieces for its determinant. So it is the minor. Okay, so 2 times 1 minus 0 times 0. And then we have the positive term up here, so we block off this L shape here. So it's 2 times 0, 3 times 0. So that's the nice thing. Okay. All right, and I think I actually got that almost to the right size. Okay. The next one, we look at 2, we knock off its row and column that it's in. We look at the minor 1 times 1 minus 0 times 0. And this one is negative as well. So 1 times 1 and 0 times 0. The next term is positive. Well, positive on the outside. Okay. So when we get positive on the outside, we're looking at 3. We're looking at its minor. It's 1, 1, 0, 0. Oh, I messed that one up for, that's right. So 1 times 1 minus 0 times 0. Then we have the negative on the next term. We take 0, and then we look at its minor. It's 1, 0, 1, 0. Okay. Then, now we're on to the last one. 0, we knock off its row and column. We look at its minor, 1 times 0 and 0 times 0. This one's positive. So we had 1 times 0 minus 3 times 0. The next term is negative. All right, so we knock out the row and column. 1 times 0, 0 times 2. And then the last one is going to be a positive term, well, positive on the outside at least. So we knock off this row and column, look at its minor, 1 times 3 minus 1 times 2. All right. So now we have all of our parts for this big C. So again, I'm going to erase this side because I want these at least to all be in one frame when we get there. So again, this is all for finding that inverse. So the augmented matrix format, that's a pretty quick way to go about it. You do have probably a multiple step process for this one, and this one has too. So you see if we blow this up, this becomes very daunting, especially this part. If we do it by cofactor to adjoint to the inverse. So this is still part 1. I'm just rewriting what we found. So big C here. So our cofactor matrix is now of the format 3, -2, 0, -1, 1, 0, 0, 0, 1. Okay, just to double check all of the math there. Okay, looks good. All right, so the next step, part 2 of this form. So this was one way to find the inverse. This is the other way. Okay, step 2 is to go through and find the adjoint. The adjoint is just the transpose of this one. So the transpose is really easy. The adjoint of psi, which is equal to big C transpose. Transpose is real quick and easy. You keep the diagonal and then alternate the position. So it's alternating rows and columns for this. So since we're dealing with a square matrix, it still stays a 3 by 3. This becomes -2, this is -1. This is 0, that's 0, and then 0, 0. So nothing really big there on that part. All right, step 3. You're like, man, if it was just those 3 steps, this would be quick. But we had to go through a big process to get there. Again, that's not that bad. Just it'll take some time, especially if you deal with a 4 by 4. All right, so we want to find Tsai inverse. Well, that's equal to the determinant of psi sorry, 1 over the determinant of psi times C transpose 3, negative 1, 0, negative 2, 1, 0, 0, 0, 1. Okay? So, our determinant. Well, the determinant of this guy, if we saw previously, we said the determinant of psi, so I'm using previous information, was e to the 6t, right? Well, we want the determinant of psi when evaluated at 0. Well, that just becomes e to the 6 times 0, so that's 1. So that's the cool part about this one. So in our case, the inverse of this is 3, negative 1, 0, negative 2, 1, 0, 0, 0, 1. So that's the cool part about this one. You can use previous information for that. Or if you went back through and found the determinant of this, you would find out that it's 1 as well. All right, so now that we've worked through all of that, I would take a second and definitely write this down. Again, what I have shown so far is a big mess, but just to get there is we wanted to find out what C1, C2, C3 are. So in order to do that, we had to find Tsai inverse first. So one way to find the inverse is either use the augmented matrix with the identity matrix and use row reduction in order to get there. That's the nice part, is it's very straightforward and we're always guaranteed it, especially if psi is a fundamental set. So notice the importance there. Or the other way you could do it is find the cofactor of matrix of psi, which is using the minors determinants for each of the terms. Then find its transpose, then take that transpose and divide and multiply it by 1 over the determinant. So that is what we have done so far. Okay, so let's actually finish this one up. All right, so we have C is equal to Tsai inverse of 0 times y sub 0, the initial values. Okay. From either way that we did this, we got 3, negative 1, 0, negative 2, 1, 0, 0, 0, 1 times 3, 7, 4, which are those initial conditions that we had here. Okay. And now all we have to do is multiply this out, and this will give us C1, C2, and C3. Okay. Row times column. So we get 3 times 3 minus 1 times 7 plus 0 times 4. All right. Negative 2 times 3 plus 1 times 7 plus 0 times 4. And 0 times 3 plus 0 times 7 plus 1 times 4. So in our case, when we get there, 3 times 3 is 9 minus 7, and it's going to be 2. Negative 6 plus 7 is going to be positive 1, 0, 0, 4, which is equal to C1, C2, and C3, respectively. All right, so therefore, now I'm going to erase this part. We have found out what our constant values are for this IVP. Again, the reason I went that long way to show you is to show you both ways to find the inverse. So I want you to appreciate one term or the other. All right. So now we're ready to say what our solution is. Thus, our solution of the IVP is the following. Y of t is equal to C1 to, let's see if I wrote it that way. Sorry. Is psi of t times c here. So in our case, e to the 2t, 2e to the 2t, 0. E to the 3t, 3e to the 3t, 0. 0, 0, e to the t. So that was our original psi. Times our constants that we just found from finding the inverse and solving was 2, 1, 4. And then so when we multiply them together, we are going to get our solution. So in our case, we have 2e to the 2t plus 1 times e to the 3t plus 0. Then 2 times 2e to the 2t, so 4e to the 2t plus 3e to the 3t plus 0. And then 0, 0, 4e to the t. And that is our solution for this IVP. And that's where I'm going to stop this video. So this is how you go about solving an IVP once you find out what the solutions are. And we are going to go through that process in 4.5 and so on. So we are going to get to, well, how do we find those? But right now, if you're given a set of solutions, first of all, are they solutions? Second, do they form a fundamental set? And then the next piece is solve the IVP if you have it. So that's it for today. Hey everybody, Mr. Brooks. One more time with section 4.3. So this is the very last part. This is just an additional observation that comes up with this. If you run across this at some point, and I think some of the homework problems are going to be based upon that. So I wanted you to be prepared for that. Also, before I talk about this, Abel's theorem, which happened in chapter 3, where we could use the Wronskian for any value of t, or we can, is the same thing as saying the Wronskian is non-zero for a specific value of t. That also applies in these situations as well. So that's the nice thing, is once you find out on that interval, you can use any value of t for that and then find its Wronskian. So then the calculations become a lot less daunting, and then it's just numbers that you're dealing with instead of functions. That's theorem actually 4.4. So that's, if you want to look in your book, that's there for you. I wanted to throw this one in here because I think one of the textbook's problems that's in there that's listed as suggested, which I'll probably select as homework as well, talks about this particular theorem in general. So I wanted to talk about it just real quick. So first of all, it has a lot of conditions that we need. So we're going to let the set y1, y2 up to y sub n be a fundamental set of solutions for our linear system on some interval a, b. Here, P of t is continuous, so that is a very important piece to this, that it's continuous on that particular interval. And then we're going to let psi equal that fundamental set. So this is the fundamental matrix that's formed. Then we're going to let this new set here, y1 hat, y2 hat, and so forth, be any other set of n solutions of y1 is equal to P of t of y. And psi hat is equal to some matrix here formed by this set. Okay? Then the following statements are true. There is a unique solution, or sorry, there is a unique constant n by n matrix, sorry, n by n constant matrix, we'll call it big C, such that if we multiply our original fundamental matrix by that constant matrix, we get out our psi hat. Okay, so that means there's something out there that we can multiply this by in order to achieve this fundamental matrix. Okay, where t is in AB. In part 2, is moreover the set y1 hat, y2 hat, up to y sub n hat is also, now this is the big kicker and also why I wrote it in this format, is also a fundamental set. Of solutions if and only if the determinant of C is non-zero. Okay, so that's the cool thing. So if you can show that the determinant of this constant matrix, whatever it happens to be, is non-zero, then that new set of solutions is also a fundamental set, which is really cool. And also that kind of goes against what we would normally do when we're dealing with scalar differential equations, where we have a fundamental set, we're done it, that's the only one. In this particular case, that might not be the situation. And so we'll actually see that when we talk about, when we get into the eigenvalue problem, that eigenvectors or eigenvalues are not always unique in that particular section. And so we'll talk about that more when we get into section 4.4 and 4.5. But yeah, this is a great observation and also will help you with some of the homework problems that are going to pop up and possibly on the Emporium quizzes as well. So I just wanted to throw this one out there so then that way you have that information. Y'all have a wonderful day.